So we're going to talk about microcontroller characteristics right now, the different characteristics of microcontrollers. Now, the reason why this is important for making IoT systems is because when you're making an IoT system, probably the first decision or one of the early decisions about how to implement the system is going to be which microcontroller should you use, right? Now, there are a wide range of choices with microcontrollers, and you're going to have to find one to use. Now, a lot of these decisions are sort of pre-done for you. Like if you work at a company, they use a particular brand, we use Freescale, whatever, that's what you use, right? But even within those constraints, you get, even if you're stuck with, say you're only using Freescale, there's a ton of microcontrollers you can use, all with sort of different properties and things like this. And you got to pick the one that's right for your project. Because another feature of IoT systems is that they are generally constrained, tightly constrained, okay? So it's not like a desktop laptop, right? If you look at a desktop, laptop, those things are over-engineered, okay? In the sense that, you know, you get some quad-core processors running at, I don't know, 3 gigahertz, something like this. Regular user doesn't use that, okay? In fact, it's running at sort of 2% capacity 99% of the time. Until you start playing a game. Okay, certain games, they will suck up that power. They will use what the computer has. But vast majority of the time, that processor is sitting there at 2%, basically idling, okay? Because you don't need 4 cores. You don't need that kind of clock rate. You don't need everything that it has. IoT-based systems, those things are cheap, okay? You want to be cheap. You do not want to buy some big, powerful microcontroller that you don't need. You're always saving money, trying to say, look, what is the cheapest thing that just barely does what I need to do? So what you need is you need to have in mind a set of characteristics that your microcontroller needs, sort of the bare minimum from your system, and then you look through the data sheets for the microcontrollers to figure out which one has that, just barely, which is the cheapest one that has that. Now, a data sheet, we're not going to look at a data sheet because those are painful to look at. But a data sheet is basically the sheet that has all the information about the particular microcontroller. So if you ever want to look up a microcontroller, you could look on the top of the chip. You could see the name of the microcontroller, its part number and everything. You type that into Google, and you say data sheet, and you will come up with a data sheet, most likely. And this data sheet, you might look at one. They are definitely complicated to read. They have lots of different details about the microcontroller. But there's certain information in there, there's certain things in there that we really need to understand in order to make reasonable decisions. So we don't have to understand everything in there, and we will not. But certain high-level characteristics of a microcontroller, you should know what they mean. And so when you look at a data sheet, say the front page of the data sheet, you can at least tell superficially, yeah, it has this, it has that, it has that. That's what I need. Oh, I don't need that, so on. So let's talk about sort of the basic characteristics of microcontrollers that you might look into. And again, also another thing let me mention is that in this class, you won't be making this decision. You're not going to be deciding which microcontroller you're going to use. In this course, we use an Arduinos, right? And then the next set of course, we can use Raspberry Pi. We're set with that. But I'm saying outside of the course, when you want to design your own IoT system, you will need to pick a microcontroller. Okay, so data path bit width. Bit width, what that means is it's the number of bits in each register. A register is a storage element that stores a number. So the bit width basically tells you the size of most numbers in your system. How many bits? So every number is represented in binary as a series of bits, which are binary digits, either 0 or 1. And the more bits, the better. Okay, so what do I mean by that? The more bits mean, if you have more bits, like 64 bits, let's say, that means you can get more accuracy than you could with 16 bits, something like that. So you get more accuracy, you get more data throughput. So basically, if you're processing on 64-bit numbers, there's more data processing than you can do than if you're processing on 8-bit numbers. Now, we're not going to go into architecture, but roughly that's what data path bit width means. Now, there's a limit. I mean, you don't need excessive accuracy in your average system, right? So, you know, an 8-bit microcontroller, like the Arduino that we're using, is based on an 8-bit microcontroller. That is sufficient. That is minimal, but that is sufficient for the tasks that we're doing in this class, right? We don't need high accuracy, right? We're just doing simple control operations. We don't need accuracy in numbers. So bit width is something you have to think about depending on the task that you're performing. Input-output pins. Now, this is actually an important thing because it's often a bottleneck. So you got your microcontroller. The microcontroller is the center of the system. It's connected to everything. It's orchestrating the whole system, right? So the microcontroller has to be connected to all the different components that you want to put in your system. Now, maybe not all, but to a lot of them, okay? And it requires pins to connect it to these things. So maybe you need 3 pins to connect to one integrated circuit and 5 pins to connect to another, and so on, depending on what the circuit is, how many pins it has on this interface. And you can easily chew up all the pins. You can easily use up all the pins in a microcontroller. Because these microcontrollers, generally, they don't have too many pins. So you have to be careful about how you use the pins. So that's why very early in the design process, you have to sort of sketch out your design, figure out what the different components are you going to use, and how many pins each one of them needs to talk to the microcontroller. And so you can get a number like, say, oh, okay, I need 40 pins. And then you can find a data sheet that reports that it has at least 40 pins and so on, right? So input-output pins are important for that reason. Performance, okay, so performance is important. It depends on the application, right? So sometimes it's important, sometimes it's not. Now, one thing to note with performance is many times when you're making an IoT device, it is interacting with a human, right? It's a device that's dealing with a human, and humans are slow. So humans, they don't need you to respond too quickly. Now, when I say not too quickly, let's say you're putting images on a screen. These images on a screen, if you put 30 a second on a screen, a human will be very happy with that. A human will see it move, everything will be smooth, right? Now, 30 frames a second, 30 things a second, operations a second is very little for many processors. And that depends on the processor. But that's maybe the processor could do a lot more than that, but it's not necessary because the human is slow. So you especially get with sound, right? With audio, a human can only hear, 22 kilohertz, I think, is the maximum frequency. That is not very fast, okay? 22,000 operations a second. It's not that's not a high rate of processor speed, right? So a processor can process audio data much faster than a human can hear the data, right? So you can use a pretty slow processor and still produce satisfactory audio. So performance is important. You have to consider that. Depends on your application. Video requires a lot more. Even though it's 30 frames a second, each frame might have many millions of pixels, and you might have to do lots of processing on that. So video generally requires a higher rate. But audio, if you're just doing audio or tactile, maybe if somebody's pressing a button, something like that, very slow clock rate is sufficient. There we go. Okay, so some other features. Timers. There are other components inside your microcontroller that are commonly useful to an IoT system, like a timer. Now, you need a timer for any type of real-time application, and a lot of IoT systems have real-time functionality in them. So say you want something to happen at a certain deadline. I want to sample this sound at, every 1,000th of a second, I want to sample a sound. Then you need a timer to trigger that event to happen at that rate, right? So, or I want to sample a monitor. I want to sample some temperature monitor at some regular period, right? You need a timer to set that, to force that to happen at that rate. So timers are really important in microcontrollers, so you need a few timers. And when you're considering the timers, there's a timer accuracy issue. You got to think how much accuracy do you need in the timing, and then that determines the bit width of the timer, right? So an 8-bit timer is less accurate than a 16-bit timer. We'll get into that later when we deal with timers. But anyway, timers are components that you look for. You always want a few of them in a microcontroller. Analog to digital converters. So what this is for is to read analog signals. Now, the issue here is that microcontrollers are generally digital devices. Okay, and when I say digital, all the numbers are zeros and one, off or on. They are discrete values. Okay, 0 or 1, nothing in between. Now, analog is a continuous set of values. So the difference between analog and digital is the same as the difference between real numbers and integers, right? They're discrete integers. You can have 0, 1, 2, but you can't have 1.5. Where analog is continuous. You can have any number anywhere. Now, microcontrollers and integrated circuits in general, they are almost always digital, completely digital. Because it's much easier to design a digital circuit than it is to design an analog circuit, but they are digital. But the world is analog. So what I mean by that, say this light that is in my face while we're recording, right? This light can be a little brighter. I hope it's not a little brighter, a little dimmer, okay? It's not just off or on. They can increase the brightness, decrease it in an analog way. So like phenomena that humans interact with, sound, right? I can talk a little louder, I can talk a little softer, and so on. So that's an analog phenomenon. So the world is generally analog to the perceptions of a human, but these computers are digital. So if you want an IoT device to process these analog phenomena, it has to convert it into a digital number. So the brightness of this light, say I want my IoT system to do something with when the brightness reaches a certain threshold. It needs to be able to take that analog value of that light brightness, convert it to a digital number that I can use in my code. I can say if brightness is greater than 1000 or some digital number, right? So analog to digital converters are important in IoT devices because you want to generally, it's very common to take analog phenomena and convert it to digital values that you can process in your code. So A to D converter, analog to digital, A to D, usually want one or more of these in a microcontroller. And I'll note right now, Raspberry Pi does not actually have an analog to digital converter. So that limits it in certain ways. But it is very common for a microcontroller to have at least one analog to digital converter. Low power modes. These are common nowadays too. When I say nowadays, I'm an old guy. So I remember back in the old days when nobody cared about power. There's plenty of power. That's because everything was, things weren't battery powered. Everything was plugged into a wall. Also, microcontrollers were just much slower then, so they didn't consume much power. But nowadays, things are battery driven. Things are fast, right? The clock rate is fast, and the faster it runs, the more power it uses. So power is a very big issue these days when you're doing integrated circuit design and system design. So in integrated circuits, it is very common to have low power modes. In microcontrollers, you can have different low power modes. So the chip doesn't have to be just completely off or completely on. It can have these intermediate modes where certain things are turned on, certain things are turned off, or maybe something is turned on but it's running at a slower rate. Things like this. Maybe you can't use the memory, but it doesn't lose what it's storing, right? So it's got this intermediate state. So there are low power modes built into these microcontrollers commonly. And we're not going to cover that in this class because that's a little more sophisticated than we touch on in this class. But more advanced IoT systems, yeah, you're considering low power modes. These things often run off of batteries. You want them to run a long time and not suck down the whole battery, so that you often want them to run in low power mode when it's possible. So you can see this in a data sheet. You can, right in the front page probably, it'll say that it has certain low power modes. Communication protocol support. So what this is, and we'll get to this more later, but these microcontrollers, they have to communicate with other integrated circuits, okay? And these integrated circuits, the way that they communicate, they use some kind of a communication protocol. A relatively simple communication protocol. The way that they send data to and from each other over a set of pins, it got to be in a certain order with a certain timing and so on. That's the protocol. And we'll get into more detail about these protocols later, but some of them are UART, I2C, SPI. Those are some, actually we'll cover those later in class, but these are protocols that you can look in a data sheet and say, yes, it supports I2C, yes, it supports SPI, yes, it supports UART, right? Now this is important because when you're making your bigger system, say you want your microcontroller to talk to some SRAM chip, right? This SRAM chip, maybe it talks I2C, but it doesn't talk SPI. If your microcontroller doesn't support I2C, then you have trouble. Now, generally, these microcontrollers nowadays, they mostly support everything, all the ones I just said, and others too. So generally, you have, in most basic microcontrollers, you have a lot of communication protocol support, but you should check just in case. Thank you.